there are two types of spec that we're talking about. Spectroscopy. Scopy is like microscope, refers to light coming through something to illuminate it. So the spectroscope or spectroscope that you use in your lab to look at the hydrogen, emission spectra, that's referring to light. And then we are going to see some spectrometry, mass spectrometry, and that's referring to actually more qualitative means of mass. So we'll see both of them. But I'm videoing good. This is the document that I have right here. It's just an intro to spectroscopes or spectroscopy. So we can't always see molecules. So we have to somehow affect the chemicals in a way that they put back light so that we can see them. That's basically what spectroscopy is working at. It's trying to influence the molecules to reflect back some sort of wavelength that's visible to us or visible to instruments that we use, like X-ray crystallography or UV vis spectroscopy. Any kind of instrument that we use is going to detect some sort of some form of energy. What are all of our forms of energy, people? Gamma. Okay, gonna extra voice in my radio. So gamma, X-ray, your voice visible in my radio. All right, there you go. Okay, so the study of light and how it interacts with molecules. Whenever the light is hit, it's going to somehow put back a different form of energy. It depends on the amount of energy that is absorbed and then released back through reflection or through re-emission. I'll let you guys read through this as an intro. But we do know that basically all matter has electrons, so as we do this, we're exciting the electrons, and as we excite the electrons, they jump up to an excited state. They can't hang out the excited state because they're unstable. The electrons fall back down to ground state, and they release some sort of energy. Not all energy is in the visible spectrum. A lot of energy, but that's in the natural world, is in the UV spectrum. And like butterflies, we talk about this. Butterflies see in UV. Yeah. So there's different forms of energy that different types of organisms can take in as well through different chemicals that they have in their eyes, right? But one different thing that we've not talked about yet is the energy that is put into the molecule can cause it to do different things. It can cause it to increase rotation, so it's going to spin faster, vibrate faster, or the electronic excitation just means that it jumps up an electron energy level and then falls back down. So sometimes we're not going to see visible light come back at us because it's not dropping electrons back from excited state. But we can measure rotational energy and measure vibrational energy through different methods of spectroscopy, like UV vis or IR spectroscopy. So that's what we're going to see a bit more today. There are other ways that we can measure these things. What am I doing? Okay. So other things that we can measure is NMR. The NMR, nuclear resonance or nuclear magnetic resonance, is a huge machine, and they're really, really, really expensive. But one example of what you can use NMRs for, I went to the Kannapolis Research Campus, and they do a lot with nutrition over there. I don't know if you guys know that. Kannapolis Research Center, they do a lot with nutrition. If you ever want to get an exercise study, they will do some exercise studies. Appalachian State has a facility there, and they pretty much are measuring the calorimetry of your metabolism. So they say, okay, we pull these probes up to you, and you're just going to run on this treadmill for like 2 hours, and then they're going to figure out, I mean, you probably get breaks and stuff, but they measure how many calories you burn based off of the different reactions that they can sense with their sensors, right? So anyway, another one that they had was they were trying to figure out the optimal amount of liquid to put in hot dog packaging so the hot dog stayed hydrated. Okay, so then they had to make these little tiny, tiny hot dogs, put it in the NMR, and test what happened when at the different water levels, what happened to the hot dog when you heated it up. I was like, wow, fancy, fancy stuff happening here, right? So they have different reasons for these different techniques and different things that they're measuring. Okay, so energy states are quantized, have a set amount of energy. We know that. This is just a lot of repeating of stuff that we've learned about already. Okay, so if we were to see something that's reflected back, it would have to be in the visible spectrum, right? We can't see anything else. We can feel other things. We can detect other things. But one other interesting field is X-ray crystallography. Marie Curie, one of the prominent female scientists. Where's curium? Curium Zone or someplace, yeah. So she did a lot with nuclear chemistry. She also has a whole museum dedicated to her in France. Solid. Okay, but she worked with X-ray crystallography as well. She actually advised Watson and Crick. What's their relevance? DNA. She advised them on, hey, maybe you guys should use this new thing, X-ray crystallography, and it'll tell you help to see what the DNA structure actually looks like. So they don't give her credit, but she pretty much answered the answer for them. They didn't know it was a double helix, they thought it was a single helix. She's like, no, here, learn how to read this X-ray crystallography image and I'll show you. And they didn't know how to read it, so she had to teach them. So she gets a lot of credit there. Not really, she should. But this one's going to be basically seeing X-rays and how X-rays coming back creates a image of the internal crystalline structure of certain types of chemicals. So it gives you more of a 3D image. The only thing is that when you are doing the crystals, if they have any impurities or contaminants in them, are worthless. The X-rays come back very scattered and does not do a good job of giving you the actual image, 3D image. Mass spectroscopy, mass spectrometry. A lot of people do say mass spectroscopy because we lump all the spectroscopies together. Mass spectrometry is something we learned about, talking about different isotopes and how different isotopes have different masses, but then we look at the relative abundance of them to get the average atomic mass. So that group working with that will give us some more information. There's a lot more to this, and they're going to tell us about that. And then I have just a couple of summary charts here. I'm not going to go through because you guys are going to do that. But at the bottom of this page, I've got the big packet that has the page numbers denoted at the top, mass spec group, lab activities group, IR Spectra group, UV group, and if you want some extra information on organic. Okay, so I'm going to give you guys about 20, 30 minutes max to come up with a short presentation based off these 3 questions and more if you want to. And you guys can work in groups of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13. Shoosh. 13. I have 5. No, do I have 4 groups? Do I have 5 groups or 4 groups? 4. Okay, then we'll do 3 and 1 of 4. Yes, Tara. Whew. You called it. All right, but here, hold on. You got on my website. You got to come to so this is the mass spec. This is the IR. This is UV. This is lab related. I don't know. Yeah, it's a bunch of stuff that we can write about. That's lab related. Okay, so let's do 20. If you want to make a Google Doc and cut and paste stuff from my documents, that's fine. Let's do yeah. I just gave you a lot. Okay. Alright, so A equals ABC. Nope. Present over there, bus chair. Yay, they're back. Present over there, bus chair.
Yeah, do you want me to stop recording?
I'll help you over there.
Allison's still on.
Shayna's not coming.
Okay.
Alright, so A is equal to ABC, right?
Yes.
Yeah, A is absorbance. Little a.
That's the C's concentration. L was white. The little E was S in our thing.
Yeah, but that equation is not so crazy.
Okay.
I told you guys I'd help you. I didn't do just make this presentation, but
Yeah.
A is equal to ABC. Does anybody remember anything? Say yes. The answer is yes.
Yes. Absorbance.
Okay. A is absorbance is equal to little ABC. Little a, molar absorptivity constant. Absorptivity, little a. Yes?
Yes.
B, cuvette. Cuvette width, like in centimeters and millimeters, really tiny. C, concentration. So, molar absorptivity constant, which is just basically constant. B is a cuvette. That's why we use the same cuvette over and over and over and over and over. And C is concentration. So, continue.
Okay. So the last part of this slide, it's basically saying that the energy difference when electrons are excited, it's going to be absorbed if the electron goes to a higher level, so like 2 to 4, and that determines the amount of difference, determines the color of light that will be absorbed.
Okay, so UV spectroscopy has like many things it can do. First, it's used a lot in like genetics, especially enzyme kinetics and like looking at DNA. It can also be used in the pharmaceutical industry, and it really just like it looks like into the products that they're like composition, and yeah, it's fun in quality control. So that's what it uses. That's what it does in pharmaceuticals. Is it tests the tablets to make sure they're like stellar.
And one thing that mainly all of us use is sunscreen.
And then,
It's also in agriculture. Forgot to mention that.
do you, where's the other thing?
Documents download.
Okay, and then,
We pause. We go back up. I'm sorry. Just a little bit scroll for me up to see what conjugated system again. Five on. Okay, with our there. Benzene, yeah. Benzene. That's called a conjugated system. Conjugated just means resonance structures. You got lots of pi bonds in different places. Electrons can you can excite the electrons in such a system, and you can excite them, and they can move their double bond. That's why it's considered to be from everywhere, not just a single particular location between two different carbons. That's going to be used a lot in like the band energy gap that Dr. Walter was talking about last week, and transferring solar energy light, aka visible light, UV light, or UV energy into a chemical system.
okay, so we wanted to talk about this and this equation. Sonia, do you want to talk about this?
Sure. Okay, so this equation basically states that the absorbance is related to the intensity of the, I don't know how to say this, but I subscript O, which is called the reference cell, which is right there, and it's over the intensity of the sample cell, which is right here, and then that's the formula.
And that's just a modified Beer's law. Don't get too crazy about trying to look it up.
And do you want to talk about the color?
Okay, come on in.
Okay, and then with the colors, this is just kind of like, we already kind of know this a little bit, but it was just kind of talking about how if you got light absorbed here, then like it would be the opposite side as what color you see, which is, we kind of already know, but that's it.
Elfin.
Let's do next group. The addition to this group is going to be more based on laboratory application, and that is our Daniel Avery Grace group. Thanks, guys. I know making these really quick, but I wanted you guys to have some time to work on FRQs. Okay. So I'm gonna help with this too, as you go through.
Don't touch. This is just the ratchetness. I just kind of went through and bullet pointed all the information.
Yeah, they had a weird assignment. They had to find applications of this in the lab.
As far as I can go, that's basically, our purpose was to tell you how Beer's law and kinetics is applied to the lab, and also go over first, second order, first order. So, yeah. So basically, okay, I'll just go. Spectroscopy is used in a lab by testing like absorbance of certain solutions, and basically it works by you have a solution and it shines a light through it, and then it records like % of what light is transmitted, and that's its
Related to concentration.
yes. So basically, the higher concentration, the more things, quote unquote things, the more light the solution will absorb, and so the absorbance rate is higher, and the transmittance is lower. That's related to Beer's law, the A equals ABC.
And for kinetics, remember the rate constant is, or rate equals K times A, B. And it's used to determine the rate of composition and decomposition in certain chemicals. And this is especially for your body, like with medicine, how fast it metabolizes in your body.
Oh, sorry.
Pause for me real fast. I'm gonna jump back to your ABC. Guys, do you remember this? Everybody, you people in front of me. Do you remember drawing your absorbance versus concentration graphs? What was this called? Calibration curve, right? So you have your calibration curve, and it's going to be used highly in order, it'll be used if you find the absorbance of something and you don't know the concentration. Once you've created a calibration curve of such known concentrations, you could go to the line, drop it down, and look at the concentration of interest. So your calibration curves are used for finding unknown molarities. based off absorbance data.
My stuff or that stuff?
Okay, so going over the rates, we already know most of this, but zero order means the rate doesn't really change with concentration. And that graph,
It's on the PDF. You just gotta scroll down
all the way down?
until you.
It's like 40 billion pages, just use
There's
this.
an arrow at the top, guys. Arrow at the top. Arrow.
Oh, right there.
Which one was it
I
in?
think it's this one.
Exercise two.
I
Yeah, I
think
think
it
this
is.
is it.
Scroll.
That one.
It's that, it's right there. Okay, so you can see that right here is what this one's weird. This is concentration versus time, and you can see that this graph is completely linear with first order. As you go down to zero order. As you go down to first order, it's the concentration is directly proportional. No, what's
The concentration change of time over time is 1 to 1.
1 to 1. So yeah. So you can see how the graph starts with a curve. So it's kind of linear, not really.
No, your other one's linear. You're right, because your labels are really tiny over there.
This
So
one.
the first graph is concentration versus time, right?
And this one's the natural log of
Natural,
concentration
yeah.
versus time.
Yeah, natural log.
So we're just looking at concentration. You can see that the graph is curved. And as you go down to second order, it's even more. It looks like an L shape. But this one is 1. This graph is 1 over concentration. So it goes up as time goes on.
Okay, so scroll back up to zero order. So I don't know if you guys remember this. I'm sure I'm gonna help them because kinetics was like what that was totally last year, right? So kinetics, we had the crystal violet lab, the purple stuff. Yes, remember this? And you bleached it pretty much with sodium hydroxide. The crystal violet was a deep violet purple, and then you added sodium hydroxide, and as it reacted, what happened to the purple color? It faded away, right? So the rate at which it fades away was allowing for us to determine the order of crystal violet in the crystal violet reaction. But the importance of light spectroscopy behind it was that we had to literally determine the amount of purple left over, which was the concentration of crystal violet. But you can't just look at it and determine the concentration. You have to use the Spec 20 or the colorimeter, which was the the visible spectroscopy component of this. So we have to be able to remember to look at data, obtain evidence of zero first or second order. ln of concentration versus time is linear for first order. Concentration versus time is linear for next order. Thank you. And 1 over concentration versus time is linear for second order. That's the one with the positive slope. Okay, we're going to jump into review after exams, but is there anything else you guys need to talk about?
She's got a real life example.
Side note, you can use when people overdose, you can use UV light to determine what concentration they overdosed at.
Right, everything's about concentration, right? So you can use this for environmental deposition of heavy metals. You can take a sample of water, do a UV vis spectroscopy analysis of it, determine the concentration of the heavy metal in water. They can do that with a lot of different pollutants that have some sort of absorbency capability. So not everything's going to absorb UV or vis very well. So that's what they'll do. You guys remember the big water crisis in West Virginia last year? They had a spill of one of their coal plants. Contaminated most of their water. Nobody had clean water. Remember that?
Yeah.
Okay, some people. Well, okay, my sister was in med school in West Virginia. I heard that for weeks, but she had to come to North Carolina and go get water. Sam's thought she got I don't know, hundreds of bottles, and she had to bring it back to West Virginia for people. So they couldn't wash their hair. They couldn't brush their teeth. They couldn't do anything. It's awful. So that's good for the first 2 groups. Yay! Next groups. Yay! It's in order, so not this one. I think infrared. Okay, infrared. This group. Okay, you guys can present.
Alright, so we did infrared spectroscopy. And infrared spectroscopy is when the bonds within molecules vibrate at all temperatures above absolute zero. Absorptions of energy increase the amplitude of the vibrations, known as resonance. An IR spectrometer detects how the absorption of a sample varies with wave number cm to the -1, which is the reciprocal of the wavelength. When bonds absorb are
Tell us about it.
Alright, so like when bonds absorb the IR radiation, like they like expand, and, like do what she's doing.
You want to do it? You ready? Let's back this out. Okay. So what do bonds do? They got lots of potential energy, right? So every particle in our body right now is doing what? Vibrating, right? All right. So we will be carbon dioxide. Ready? All right. So we need to have some stretching vibrations. Okay. And then on one side, and the other side. Okay. And then stretching. And then they have this other thing that they do.
No one better be videotaping.
They also do this, right? Don't they do this? What's this? Bending. They bend.
I'm stopping this new
I told them we were going to dance for this. Okay, tell us more about this vibration stuff you're talking about.
Alright, so like the vibrations, what they'll do is they'll like make it have temporary dipoles instead of just being like carbon dioxide. Instead of being a non-polar molecule, it has a temporary dipole due to this stretching and vibrating and shrinking and stuff. So, and that's what it's saying when the bonds absorb the IR radiation, they vibrate and stretch. And then an IR spectrometer passes IR through like the full IR range, which is all of the different wavelengths of IR light. And it can be between like two different plates, which it usually is because it can be liquid between two different plates. It can be a solution, a mixture in between like some special cells. And it can be like a paste, like kind of like toothpaste or something like that. Or it can be like a solid mixed with potassium bromide in a disc form, like flattened into a disc form. And there's a picture on page 3 that will look out like.
Okay. I want to interject real fast. For IR, they're talking about infrared energy. Yes. IR lower energy than our UV vis group. Lower energy. So UV vis group, they were like literally slamming their molecules with energy, and the energy would excite the electrons would jump up, fall back down. This is not as much energy. So it just gives them a little bit more energy in order to vibrate. It's not going to cause the excitation of electrons necessarily. Okay, so that's why this is different than our UV vis.
Okay. Can I go ahead and pull up a picture for this one?
Yeah.
It's easier to explain with a
Yeah.
picture.
It's on that PDF down there.
Do you want to show the picture?
I will when this is.
Oh, here, go back up. Those are our stretches we are doing: symmetrical, asymmetrical, and bending. It's like an exercise class, guys. Okay.
Okay. And then there are different factors that affect how it bends. I did? Oh, I didn't realize it was in color. Okay. The different types of effects are, like, you can think of it as a spring. Like, you can pull the spring and you can bend it, and whichever, like, pulling it takes more energy than bending it does. And it's the same way when, like, the molecules bend or stretch. And then the strengths are sort of like the triple bond is stronger, so it'll take more energy to pull it as far. And then the single bond obviously doesn't take as much energy to stretch it. And then this one was kind of confusing, I think, but like you can just think of the mass of each atom as like a weight on the end of the spring, so it affects how it pulls and bends.
So the ones that vibrate the most are single bonds, and the ones that stretch the most are the heavier bonds between a light and a heavy molecule. I mean, atom. Sorry, atom.
This was the picture from the first page. It was just from a actual lab with ethanol. It was the transmittance versus the. I want to say that was wavelength.
This would be IR piece.
Oh. Then. Oh yeah, I already showed the other one. I don't know how to present that again.
Go close to share. You see share?
I'm struggling. Yeah, go ahead. There you go. There you go.
Okay, and then why do we need infrared spectroscopy? It's used. A lot of times it's used to like identify complex molecules, And usually when you have your spectrum, you compare it to previously measured molecules, and then you use that to identify your unknown molecules from your sample. And then because of CO2's temporary dipole moments, it absorbs infrared radiation from the sun and is a key factor in the greenhouse effect.
Okay, can I add to that? So, the sun puts forth UV and visible light. It hits the earth. The earth absorbs some of it. It absorbs some of the energy. The remaining energy is IR energy, which tries to reflect back out of Earth's atmosphere. But IR, it's lower energy because, we took out some of it for like photosynthesis and stuff like that. And it's reflected back as IR, but IR gets caught in the big layer of our atmosphere, specifically the carbon dioxide. So the more carbon dioxide we put in the air, the more IR that it absorbs, the hotter our atmosphere gets, because there's not a release of the excess energy that the sun has put forth to the earth, right? So that's a big factor. Like, I'm really glad you guys put that on there. It's a big factor for the greenhouse gas effect. And then we go back to the picture that you had that pulled up, the ethanol one.
Yeah.
This is something you guys will have to observe in organic chemistry labs. Okay? So, zoom in. You see zoom at the top? Get at maybe one a little higher. Okay. So the peak, that's the downward peak, it's a peak between, what is that, carbon and oxygen? Yeah, I'm sorry, oxygen and hydrogen. You see the highlighted pinkish part on the molecule? The highlighted pink part on that peak itself is saying that it's a big stretch, a big IR stretch between oxygen and hydrogen. And then the blue stretch is between oxygen and carbon. Well, they're about the same masses, right? Grant, can you point where that peak ends on the blue one? It's a little lower, right? So it doesn't stretch as far as the red one does, just because they're similar in their masses. And then on the other side of the molecules, the carbon and hydrogen, and they stretch even less. I think so. But what you would do is you would run an IR spectroscopy scan. You would get a sample, unknown sample, and you have to identify it based off that. So they have standard peak sizes, like, this length of the peak is a CH bond, this length of the peak is a CO bond, this length of the peak is a OH bond, and you have to identify it based off data. So you guys will see stuff like this in college. Okay. Anything else from y'all?
I think we had one more page actually.
Okay.
Alright, so it's used to identify the structure of complex molecules in space, out there in space. And then it determines the time scale of the folding of complex protein structures into functioning biological molecules. And breathalyzers look for absorptions around 1060 cm 1 minus, which is the vibration of the CO bond in ethanol. I can't read today.
No, it's just how you present it.
So this is really, really important for identifying literally any bond in a molecule, and you can identify it. If you have previous samples, it's really hard to make your own samples. Too soon, good job. Thank you for dancing. Last group. Mass spectrometry. I can zoom. Yes, I can. Oopsies. Well, is that good?
Yeah,
Okay.
No? Okay, so we had mass spec. Go for it.
Okay, so what is it used for? It provides information on molecular mass and structure, and this comes in handy a lot with isotopes because there's a lot of different isotopes for different molecules or different atoms, and so this helps to identify them. They're 1,000 times more sensitive than IR or NMR, and it analyzes extremely small samples, usually on a nanoscale.
Okay, so how it works, just a little bit of background. Any wire carrying electrons produces an electromagnetic field from the flow of electrons, but an electromagnetic field can also be created by a flow of positive electrons, and that's actually what a mass spectrometer is.
So positrons.
Positrons, yes.
So the sample is vaporized, so it can move freely. So if the sample is a solid, it has to be a gas for this to work. So the sample is then ionized with high energies of electrons from an electron gun. It knocks off and forms positive ions, and okay, so then the moving positive ions are deflected by a strong magnetic field, and
Okay, so I'll just go for it. Okay, so basically the the ions are then accelerated by an electric field and focused into a beam, which are passed through different slits with negative potential, and then they're deflected by a electromagnetic field, and how much it is deflected depends on the mass to charge ratio. So the lighter the ion, the more it's deflected, and the larger the magnitude of the charges, the more it's deflected. So a calcium ion would be deflected more than a sodium ion, basically. And then detection, as the ions arrive, they gain back their electrons to become neutral, and what's actually measured is the movement of the electrons towards the ion.
so a good
So
way
here's a picture.
a good way to remember the process is vector is a daft duck.
You're getting ahead of me. Stop.
We'll show that on the document itself.
Yeah.
If you want to pull up the document. Is that the same picture of the document?
No, I found this online. So the sample is put in over here, and it's heated to vaporize, and then an electron beam ionizes the sample, and it's accelerated through the magnetic field. It's deflected, and then it hits this little plate where it gains back its electrons, and it's based on the mass charge ratio. There's that, because you know he gave us. Yeah. All right, let's see what the. Okay. I don't know where it is. Yeah. Okay. Nope. Or that works. Top, down. There we go. Okay. So, like we said, it's used to show molecular mass and structure. So that looks like fun. Not really. Oh well, not really. So okay. So there's the Victor's Daft Duck. There, go back. Up.
This is the isotopes that we were talking about. So, like, this is the most common, well, for this example, the most common isotopes for chlorine are chlorine 35 and 37. And so it's just showing you for the peaks. Oops, I just pressed something wrong. Oh, what did I do? I'm so sorry. I was trying to just scroll. Okay. So then this shows the peak for chlorine 35 isotope, and then this is 37. And the reason why this down here is at 70 is because this is diatomic chlorine, and so then it just succeeds like that.
So the M over Z is the mass to charge ratio. The ratio of charge is Z for some stupid reason. And here's ethanol, which is a biologic, which is a more like, it's an organic.
And so large molecules, they fragment. When they ionize and heat them up, they break apart. That's why there's multiple fragments. Each of those little peaks mean a different fragment of the ethanol compound of different isotopes of the CHs and O's. So there's lots and lots and lots of peaks for molecules, but like relatively few peaks for atoms.
Yeah, because this is the only peak here that's actually ethanol as a whole. The rest of them are just parts of ethanol. I'm just going to go back to that. Okay, so an application of mass spectrometry is liquid chromatography mass spectrometry, and it allows complex mixtures to be separated by liquid chromatography. So it's used in pharmaceuticals, which is allows you to identify and test different like medicines, and then this tests proteins, I think.
Yeah. It's used like to like test digestion products.
Cool.
So it's just breaking down. Anything breaks it down. It's process. solid state, and now this is just some gas. But you will do some organic lab in college. Yes, you'll do gas chromatography and living chromatography, and this will be some of them. Do you remember anything about the astrochemistry? That was the cool one.
The astrochemistry, it's used with satellites. I think I know Hansel knows more about that than I do.
Robots. They sent a robot.
To Mars and
Mars
to other
and
planets.
The rover.
Yeah.
Yeah.
Okay.
And they collected samples to determine the atmospheric conditions.
Oh, they did it. Oh, that's cool.
And then the high res is it's to distinguish compounds of the same nominal mass, which is like an approximation. It's like it's not the exact, like it's like we say hydrogen is about 1 when actually it's 1.008. So it's stuff that has about the same mass, but the actual mass is different.
Cool part is it can analyze drug and body tissue at a DNA scale.
Oh yeah. Alright, so this one's the only one that does not have what component involved.
Concentration.
Oh,
Oscopy.
that's what I'm looking for. I'm looking for light. This is the only one with no light. This one, I mean, it still doesn't have concentration involved, but it doesn't have light involved. Everything else has some sort of energy form involved. Yay! Oh, and picture. Thank you. Good job, guys. Okay, there are 15 minutes left in class. I'm glad that you guys had a chance to learn everything from each other. The people who are not here, there's a document on my webpage. You guys can read through the intro, and the video is still going. Let me go ahead and pause that.